So the standard fin types that exist really can be categorized as constant cross-sectional area fins, and of those constant cross-sectional area fins, there's sort of an easy case, which is called the pin fin, and variable cross-sectional area fins. We're going to spend some of our time really understanding constant cross-sectional area fins because we get really the insight that's required for these for all fins from these types of problems, and it's a much easier analysis. So the simplest type of constant cross-sectional area fin might be considered the pin fin, and we'll contrast this and we'll see that there are similarities between this pin fin. It looks like a pin, long, slender, cylindrical rod, as compared to, and this is again another type of fin, which you imagine that you have a wall, and protruding from this wall is some sort of rectangular object, and so there are fins of this rectangular cross-sectional area, just as well as there are these pin fins, which are this cylindrical cases. So there are different types of cross-sectional areas that you can consider for these problems. And I point out that the pin fin is an approximation for example, a temperature measurement device. It might be, for example, a thermocouple type device or a thermistor type device. So you might have a temperature measurement device where the detector, for example, could be at the tip, but the elements of the construction allow for heat transfer and conduction to occur all along the axis. And so imagine that you have one of these devices and then you insert it into, these are supposed to be blocks of ice in water, and you have air above, and the air, for example, might be at 20 degrees Celsius. The water is at 0 degrees Celsius. This is your measurement location, but that measurement location might be affected by axial conduction. So you have 20 degrees C air here, and there's a heat transfer coefficient to this T infinity, which is air, and then you have a heat transfer coefficient in the water and this temperature of the water. So to understand this problem requires an understanding of fin type analysis. Sort of more standard in fin analysis might be the case where you have multiple fins, so a whole area that's covered by fins. And eventually we want to understand how to analyze this type of system. We'll see that really it's just an energy balance that's going to allow us to deal with problems like this. A problem that I think is sort of interesting is one in which the fin analysis is being used for a problem where we're not explicitly trying to change the heat transfer area, but we're simply trying to understand how a slender rod might impact heat transfer processes. And that will come shortly. But to do all of this, let's again start talking about what is required for the fin approximation and these fin analyses. So the fin analysis requires an energy balance. So much of what we do in heat transfer is based upon energy balances. You can call it power balances, and because it's mostly on a per unit time basis. And the basic rule is, as we've I think talked about, is the amount of energy that's transferred in minus the amount of energy that's transferred out is equal to the amount of energy that we store minus the amount of energy that is generated. So some sort of generation rate. So again, in minus out is equal to storage minus generation. The problem that we're focusing on here is considered to be in steady state. So we're looking at a case where, that's interesting. Let's go back. We're looking at a case where there is no time rate of change in the properties and there is no generation. So for the case where there's no generation and it's in steady state, we're simply looking at an energy rate in minus an energy rate out. Now, for this fin, the cylindrical fin of length L that we're seeing right here, we extract from it a differential thickness element. So by differential element thickness, we're saying that there is some delta X thick element in this fin that we're going to consider and analyze. We expand to look at it, and we recognize that there's conduction in at the location X. There's conduction out at location X plus delta X. And there's convection out, and the convection out has the form of Newton's law of cooling. Now, as we look at this convection out, we clearly recognize the heat transfer coefficient. We've talked about this before. And we know that the amount of power that we're convectively transferring is proportional to the heat transfer coefficient, and it's also proportional to the surface area. So the surface area shows up here as this P delta X. P, let's note, is the perimeter of this fin. So for the cylindrical case, it's just 2 pi r. Delta X is the thickness of this differential element. So again, the surface area would be the perimeter, 2 pi r, times delta X. And of course, it's proportional to the temperature difference, T minus T infinity. So when we put this into our balance equation, we have our in term, this Q double prime AC delta X. Let's erase that so we clearly see it. So this is in. Notice that we are working with fluxes times area. So flux times area in, and out, there are two terms out. There is the conduction term out and the convection term out. So this is the conduction piece, Q double prime AC at X plus delta X. And here is the convection piece. So, as is typical, we use a Taylor expansion and Fourier's law. Let's just remind ourselves what these things mean. So the Taylor expansion, or another way of saying it is the definition of a derivative, is the fact that if we had a function f, then df dx by definition, by construction, is f of x plus delta x minus f of x divided by delta x in the limit as delta x goes to 0. So that is in fact the definition of a derivative. And as you'll see here, that's what we did with the in conduction term and the outconduction term. So both of those together in the limit of delta x going to 0 are the derivative with respect to x of q double prime AC. Now, further, we invoke Fourier's law. And remember that Fourier's law says that the heat flux is equal to minus k dt dx. And we put some limits and cases, considerations on what that means. So this is for an isotropic case. We're using the ordinary derivative because this is a steady one-dimensional problem. All right, and further, let's just understand why we did what we did here. We chose to specify this problem as being one-dimensional, and this is important. It's valid when the diameter of this fin, d, is much smaller than the length of the fin. So d over L, is small. So what that establishes is that the heat transfer is primarily in one direction, and the BO number is also small. And that statement about the BO number, let's remind ourselves what the BO number is up here in the top left. The BO number is the heat transfer coefficient times a characteristic length scale, in this case the diameter, divided by the thermal conductivity. And the way we want to think about that is that it's a measure of the conductive resistance divided by the convective resistance. And another way of thinking about that is that it's the measure of the temperature difference in the transverse direction divided by the temperature difference between the surface and the reservoir adjacent to it. So you might think about this as the convective. So what we're really saying is that while the heat transfer rate might be considered, there's some heat transfer rate in the axial direction and some heat transfer rate in the radial direction. When we look at the radial direction heat transfer rates, and these are in fact equal, that the balance says that you have a relatively small conduction resistance and an accordingly small conductive temperature difference, and these are balanced by a relatively large convective resistance and a relatively large temperature difference between the surface and the free stream. And we'll talk about this in a little bit more detail. So the next logical place is to discuss what the solutions look like for these problems. And for that, we'll go to this next section.